Welcome, everyone. Thank you for joining our November webinar of the Ocean Climate Solutions Innovation Exchange. My name is Liliana Bastian, and I'm Program Officer at Ocean Visions. I'm based with our partners at the Georgia Aquarium, and I work on our programs with the UN Decade of Ocean Science. So we do have some new people on here today. So for some quick background, the Innovation Exchange is an initiative of the UN Decade Collaborative Center for Ocean Climate Solutions, which is hosted at Ocean Visions. We're a thematic collaborative center working to advance recognition that the world's oceans are an underutilized tool for climate change mitigation. And we want to identify opportunities for people to communicate across science, tech, and policy, and also to collaborate across sectors to change that. And so the Innovation Exchange uses online and in-person events to bring emerging innovations in ocean science and technology to a broader global audience. So we've always had someone from every region of the world attending these webinars, which is something I'm really proud of. We also try to improve ocean literacy in this area, and perhaps most importantly, hear from the people who are working either on the ground or in the lab about what's needed to advance the field of ocean-based climate mitigation. So Ocean Visions is a field-building network organization advancing the research, development, and policy frameworks needed to mitigate climate change through its agenda, which focuses on emissions reduction in ocean-based industries, of course, ocean-based carbon removal, ecosystem repair, and then outreach with priority audiences and decision makers. So today's webinar is the second in a short series of sessions that we're doing on measurement, reporting, and verification, or MRV, for ocean-based carbon dioxide removal, or CDR. So as I mentioned, carbon removal is one of Ocean Vision's focus areas. And along with exploring the different pathways and developing the technologies needed to remove carbon from the oceans, we also need reliable ways to measure and verify that removal, which can be really challenging to do at all in a system that's as dynamic and complex as the oceans, let alone consistently across ocean-based pathways for CDR. So audiences from our past webinars expressed really strong interest in the topic of MRV. And back in October, we had a big picture session with representatives from Carbon Plan and Frontier to introduce us to the basics of MRV for ocean-based CDR and look at scaling advancements with demand-side market mechanisms. So that recording is on Ocean Vision's YouTube channel if you'd like to take a look back at it. And today, we're digging a lot deeper into the science with two startups on the supply side of carbon removal, Equatic and Captura, who have both recently released their MRV methodologies, which, Nikhil, would you mind putting those in the chat? Thank you. And we'll be learning about their approaches and progress and challenges in advancing MRV in the ocean CDR space. So from here, we're going to have two 15-minute presentations from each speaker, who I'll introduce in just a moment, followed by about 20 minutes for a Q&A moderated by Nikhil Neelakantan, who is Senior Program Officer at Ocean Visions, who leads our work in startup advising. And please do use the chat function to introduce yourself or connect with others who are online today, but put your questions for the speakers in the Q&A. And definitely make use of the upvote feature in there so that we can kind of see which questions are popular and most want to be answered. So the webinar is being recorded, and along with all of our other webinars, will be posted to Ocean Vision's YouTube channel within a couple of days. So let's see, I am really excited to introduce our speakers today. We have first Dr. Erika La Plante, Assistant Professor of Material Science and Engineering at UC Davis, and co-founder and head of MRV, an environmental impact assessment at Equatic, followed by Dr. Sophie Chu, who is Principal Oceanographer and Director of MRV at Captura. And they're going to share some of their work with us. So Erika, I'll hand it over to you to get started.
Thank you so much, Liliana, and I'm very happy to participate in this webinar. So today I have a few slides to talk about Equatic and our strategy for high-quality carbon dioxide removal. Equatic is really motivated by two major global challenges that we face today. We need to reduce our reliance on fossil fuels at a manageable cost while societies are still improving their living standards by using energy. And then at the same time, we also need to remove CO2. All IPCC scenarios require gigatons of CO2 removal at a manageable cost that also is measurable, permanent, and additional, while avoiding negative impacts on ecosystems and arable land. So with these two major challenges, this arises two new industries. You have the carbon dioxide removal and energy decarbonization. And both of these industries are projected to grow in the next couple of decades. So why the oceans? Oceans has a vast capacity. It uptakes about a quarter of our annual CO2 emissions. There's various technologically enhanced pathways that accelerate the CO2 storage. This includes increasing the growth of marine plants, or increasing ocean alkalinity, or the electrochemical separation of CO2 from the ocean, followed by CO2 sequestration. It is important to consider that the same ocean-air equilibrium that allows the oceans to absorb the CO2 emissions also implies that the deliberate removal of CO2 from the atmosphere requires that some of that CO2 removal will be partially offset by ocean degassing. And this one model shows, for example, 100 petagrams of carbon that has been removed at a pulse removal will result in ocean degassing, such that only about a quarter of that originally removed CO2 is actually permanently stored. So this makes it important to consider strategies that not only remove CO2 from the atmosphere, but also increase the ocean's capacity for CO2 removal, or CDR. So Equatic is a simple, scalable, permanent CDR solution. It's really composed of 3 steps. First step is the electrolysis of seawater, where we use renewable electricity to split seawater into 2 streams, also producing hydrogen and oxygen. The stage 2 is a direct air capture step, where the carbon dioxide from the atmosphere, already dissolved in water or coming from the atmosphere, is converted into dissolved inorganic carbon and also calcium carbonate solids. And then the step 3 is the permanent storage. So this carbon that has been sequestered in that water as ions or as solids is then stored, can be stored either on ocean or on land for at least 10,000 years. Yeah. And this process not only produces CDR, it also produces green hydrogen. So you can see that the hydrogen that is produced is carbon negative as compared to other types of hydrogen generation. Okay. So I'm kind of looking more closely into the process and how it works. So Equatic really accelerates and amplifies the ocean's natural ability to sequester and store CO2. We start with your oceans, so seawater intake. By passing an electrical current to the seawater, this produces 2 streams, an acidic stream and a basic stream. In the basic stream, the calcium that is already dissolved in that water and combines with the CO2 already dissolved in that water to form calcium carbonate. We also produce magnesium hydroxide in this basic stream, and then to cause the CO2 removal, this magnesium hydroxide is dissolved in seawater, and that causes the speciation of CO2 into bicarbonate and carbonate ions. There's also here that we produce hydrogen. And then on the acidic stream at the analyte, this is used to realkalinize the stream. So we use it to dissolve rocks. And what that does is it replenishes the divalent ions in that water and replenishes the alkalinity. And then the neutralized discharge is then returned back into the ocean. Okay. So looking at the mass balances of the process, so we think of this as a combined ocean and air removal. We start with seawater. Seawater contains 2.6 millimoles of CO2, dissolved in organic carbon, 11 millimoles of calcium, and 55 millimoles per kilogram. And the stage 1, which happens within the electrolyzer, is a direct ocean removal, where the DIC on the water and the calcium in the water produces calcium carbonate. And then the magnesium then also transforms in a solid to form magnesium hydroxide, that's 3.2 grams. And then in stage 2, where we have an aerator that is inside the battery limit of the plant, so we do the CO2 equilibration within the plant. This causes the precipitation of the residual calcium that is still in that catholytes from stage 1. So that all precipitates out as calcium carbonate. And then this also causes the dissolution of magnesium hydroxide in that water. And that dissolution then results in speciation of your CO2 to form bicarbonate and carbonate ions. So in total, we sequester 4.6 grams of CO2 per kilogram of seawater that is processed within this catholyte. So it's really presenting two unique pathways. So we immobilize CO2. The ions are stable for at least 10,000 years. Solids are stable for millions or even billions of years. Okay, so now we go into our MRV, and this is in that document also that Nikhil showed. So how Equatic quantifies and verifies our CO2 removal. It's really this basic equation where we have total carbon removal is equal to the drawdown of CO2 minus the emissions associated with the process. So total removal is the net extent of CDR that is caused by our process. Drawdown CO2 is the sum of the dissolved CO2 and the solid CO2, both sourced from the atmosphere that is permanently stored. And we quantify this using multiple on-stream real-time sensors, and also we have additional offline sensors so that we have redundant measurements that also increases our certainty. And then this, we have to subtract our emissions. These emissions include net embodied CO2 emissions from materials and energy used. This is primarily electricity to operate and maintain the electrolyzers, as well as the balance of plant. It also includes grinding rock, if that applies, transporting of that ground rock, as well as building Equatic's CDR plant itself. This schematic here shows the various measurement points that we have pertaining to the measurement of CDR. So we have other measurement points that's related to EIA. They're not shown here. Before, in terms of CDR, we have liquid phase analysis, gas phase analysis, and solid phase analysis. So liquid phase analysis includes measurements of dissolved inorganic carbon, measurement of elemental compositions, including magnesium and calcium concentrations, alkalinity, pH, and temperature. So you could see from our seawater influence and the solutions coming out of the catholyte and then after the processing, so we can compare those values and calculate our CDR down to the gram. The gas phase analysis also is a redundant measurement, and the solid phase analysis will give us the amounts of magnesium hydroxide and calcium carbonate that we've produced. And by comparing these different measurements, we can make sure that the mass balance is closed and we have redundant quantifications. In terms of measurements for EIA, we will monitor and sample our discharge to make sure that they meet regulatory requirements for safe discharge. So I'd like to point out here is Equatic is intentionally designed and engineered so that we can measure the CDR that has occurred within a closed system. And in terms of reporting and verification, we will follow this governing principles. Consistency, meaning that we apply the same standards across reporting periods so that we can ensure comparability between these periods. Prudence, meaning that we use fact-based data. We don't use speculative estimates to generate carbon credits. The drawdown is quantified directly by sensors, and the emissions are based on the actual recorded energy used by the plant. Transparency includes publishing publications of our project documentation that shows the total amount of CDR, having a registry in the database of carbon credits that has been retired as well as our MRV methodology. We will match the drawdown and emissions. These are the two terms in our equation for the same reporting periods, and we will use this principle of conservativeness when we're choosing approaches and assumptions that we use for the carbon accounting. So in terms of verification, we work with an independent auditor to verify our CDR. This MRV methodology also will, so the MRV methodology, and we ensure that it complies with ISO standards that make sure that we have procedures for the MRV. In verification, the activities conducted within the system boundary will be reviewed, as well as the data generated by Equatic plant operations. It includes all the data from sensors, meters, sampling, documentation of the inputs used within the system boundaries, and the evidence of any retiring credits, and making sure that we have record keeping and that standard operating procedures are adhered to. And in terms of environmental reporting, an EIA and environmental impact assessment will be prepared for each project. So this EIA will really detail discharge characteristics, monitoring requirements, and the reporting period that's specific to that jurisdiction and site. Yeah. So currently we are operating 200 kilogram CDR per day pilots since March of 23, one at the Port of LA and one in Singapore. And we are on track for a 10 ton per day or 3,500 tons per year CDR in Singapore in July of 24. So Equatic gives high quality engineered CDR that is measurable. We've intentionally designed and engineered this process so that we can measure CDR within a closed system. This means that we have continuous and unambiguous data about our process performance, and we can monitor our CO2 removed at any point in time. It is verifiable. We follow an ISO methodology that provides rules for eligibility, monitoring instructions, verification parameters, so that ensuring that there is a net negative CO2 and that there is an auditable record of this whole process. So Equatic is a permanent CDR solution. Source CO2 is mineralized bicarbonates. Aqueous bicarbonates are stable for at least 10,000 years. Solid bicarbonates are stable for up to billions of years. And it is additional. That means that the plant commissioning and operations of Equatic depends on the sale of CDR, which means that every ton of CDR is additional and credible. So as in any new industries with this rapidly growing carbon market, is important for transparent. It is important that these technologies are transparent and credible to build trust with buyers. So how we do this is we use data to generate our carbon credits. And in terms of environmental impact, Equatic process complies with existing environmental permitting regulations, and we are performing environmental impact assessment. We've performed a desktop assessment of potential impacts of the discharge of the solid and aqueous carbonates. This is something we work with third party as well. We are working on hydrodynamic water quality and particle tracking to assess magnitude and radius of impacts associated with potential perturbations in the seawater caused by aquatic discharge. This includes pH, toxicity, any sedimentation changes at the site of discharge. And then this EIA also will inform how we can optimize that discharge from the facility so that we can minimize environmental impact. So where we are now, so 23, we are operating pilots. In 2026, we're on track for a commercial scale plant, 100,000 tons of CO2. And our goal is in 2028 for 1 million tons of CO2 per year. So at this scale, really, the hydrogen that is co-produced with this process is enough to offset production costs. And then if we replicate this 1,000 times, and we get a truly gigaton scale removal. The advantage of this process, because we have two valuable co-products, CDR and hydrogen, this allows our process to be to operate at a lower cost, drastically reduce our cost, and also increases our near-term scalability. So to summarize, Equatic powers the green economy. We couple seawater electrolysis with carbon dioxide removal from the atmosphere with the generation of green hydrogen at the lowest cost. So I'm looking forward to the discussion today. Thank you.
All right. Thank you, Erika. That was really, really interesting insight into your closed system approach. I loved hearing about that. And also the kind of exciting note that you left on the scalability part and what you have coming up in the next few years. So thanks a lot. Sophie, I'd like to invite you to share your screen and get started when you're ready.
All right, well, thanks Liliana and Ocean Visions for organizing this webinar and inviting me to speak. My name is Sophie Chu. I'm the Principal Oceanographer and Director of Monitoring, Reporting, and Verification, or MRV, at Captura. We are a marine carbon dioxide removal startup company based in Pasadena, California. For my presentation today, I'll briefly introduce MCR, marine carbon dioxide removal. I think everybody knows what that is, but I'll just touch on it really briefly for those who don't, what it is, why it's important, and then I'll describe Captura, how our technology works, and what we plan to do for MRV. And then, I'm happy to answer any questions at the end. So, let's see. Okay, so Erika did a good job of talking about the global carbon cycle, so I kind of hoped that she would do that, so we could just jump into a little bit more of the CDR. Um, and so basically, I just want to say, to limit global warming to 1.5 to 2 degrees by 2100 and avoid the most severe impacts of climate change, we have to have a drastic reduction in emissions, and also start to remove carbon dioxide from the atmosphere. And that CDR can address the sectors that are difficult to decarbonize, such as shipping and flying. And it can also tackle historic emissions that have to be removed to achieve net zero and net negative emissions. And so if we're going to remove gigatons or billions of tons of carbon dioxide, we need to be able to do it safely and responsibly. This figure is from Carbon 180's publication from this past summer. It describes multiple different MCDR approaches, biological ones such as seaweed farming and nutrient fertilization, and chemical ones such as ocean alkalinity enhancement and direct ocean capture. So in direct ocean capture, CO2 is removed from seawater and permanently stored in geological formations to allow more CO2 to be absorbed from the atmosphere. That's direct ocean capture can locally mitigate ocean acidification because that CO2, that seawater that is released back to the ocean is slightly elevated in pH. This could be useful for industries that would benefit from higher pH, such as aquaculture farming. And then, Erika talked about this as well. Different methods are generally evaluated using some of these metrics, such as scalability, durability, cost of per ton of removal. So scalability means how quickly can we replicate these projects annually, and what is the theoretical cap of potential removal? So if you're thinking about seaweed farming, the theoretical cap is like, you could think about, I think maybe Ocean Business has these numbers. How much seaweed do you have to grow to get to gigatons of CO2 removal? Do we have that much space? And those kind of questions. And so we also want to find solutions that will keep CO2 out of the atmosphere for a long time, methods that have long storage times over thousands of years. And then lastly, a low cost per ton of removal will help facilitate implementation. And ideally, the method would be, an ideal method of CDR would be low cost, scalable, and have long-term storage. So we believe that Captura meets those criteria. And now I'll dig a little deeper into Captura and our technology. So Captura started off as a spin out of research by two professors at California Institute of Technology, or Caltech. Captura's approach was designed with large scale and removal in mind. So our process has two inputs, seawater and electricity, and two outputs, CO2 depleted seawater, and then CO2 that can be sequestered or utilized. We do not create any other byproducts. Once scaled up, we expect to hit the Department of Energy's target of less than $100 per ton of CO2 removal. In the near term, our strategy is to deploy with existing infrastructure, such as desalination plants or utility power plants or decommissioned oil and gas platforms, so that we can use that infrastructure to re-inject the CO2 back down the pipeline into the reservoir where the oil and gas was removed. We've been vetted by multiple industry experts. The foundational research from Captura was funded by ARPA-E, a DOE program. We're a milestone winner for the Carbon Removal X Prize, and the Frontier Climate program pre-purchased 500 tons of CO2 removal from us last year. So, and then lastly, I just wanted to say our business model is licensing so that we can focus on the R&D and license the technology to others in order to scale it faster, because I think everyone here probably realizes how this issue for carbon removal, we need to start scaling as fast as possible, but also keep doing it responsibly and safely. So, so now this is a bit of an overview, and I'll do another detailed slide in the next slide. So we draw in seawater that has a pH of about 8.1, which is the average surface ocean pH, and then we strip the CO2 out. That CO2 is measured accurately, and we can then sequester it permanently underground or reuse it. And then the CO2 depleted seawater is returned to the ocean at a slightly elevated pH of around 8.5 to 9, because that CO2 was removed, and now that water has the capacity to absorb CO2 from the atmosphere at an amount equivalent to the quantity that was removed during our process. So over time, ocean circulation will cause that discharge plume to move, and then it will get diluted and spread over a large area. as the ocean and atmosphere re-equilibrate and absorb CO2 from the atmosphere. So now to get into the details a little bit more, so our process works similarly to a desalination plant where there's a constant flow of seawater going through the system. And that's what, can you see my cursor? That's what this kind of part of the bottom is showing. So about 0.5% of that water is diverted and softened. So we're removing calcium and magnesium ions to avoid scaling in the electrodialysis unit. It's added in back, those are added in later before the discharge into the ocean. This electrodialysis unit is where Captura's proprietary membranes will be that will increase the efficiency of the process by 7 to 10 times. This is where an electric current is applied to split the water into acid and base. The acid is added into that main stream of seawater to acidify the water to about pH of 4. And then that is when the water goes through this membrane contactor and the CO2 is stripped out using a vacuum. Then that base that we had generated from the electrodialysis is added back in. Those ions that we removed before are added back in. And so now you have CO2 depleted, slightly more basic seawater that you return to the ocean to absorb CO2 from the atmosphere. So I mentioned briefly before, our near-term commercial deployment plans are to repurpose existing infrastructure and take advantage of processes that already move large volumes of water, such as desalination plants or utility plants that use water for cooling. This helps us save energy and infrastructure costs associated with pumping water. We're also interested in deploying systems on decommissioned oil and gas platforms where there's already access to a pipeline and geological reservoir to sequester CO2 from our process. Over the long term, we envision standalone systems that can be built offshore alongside renewable energy from wind or solar. These commercial systems that will range anywhere from 10 kilotons or 10,000 tons to 1 million tons per year. And so this is, talking about the future. And then so our where we are now is our piloting phase. So our first pilot was 1 ton of CO2 removal per year, and it ran for about a year at Newport Beach. We were able to achieve 90% purity of CO2 gas stream and 90% CO2 extraction efficiency. This pilot, along with our second pilot of 100 tons of CO2 removal per year, are now set up at the Alta Sea at the Port of Los Angeles in San Pedro, California. Alta Sea is a nonprofit organization that uses historic warehouses at the Port of LA to support scientific collaboration and advance the blue economy. This is the site of our proposed research to evaluate the impacts of our technology on the ocean and develop MRV, and that I'll explain a little bit more in my later slides. And our third pilot, which was recently announced, will be 1,000 tons per year and installed in Norway in a partnership with Equinor next fall. And then after this, we expect to be building commercial plants by 2026. And then on the right side of this slide, excuse me, I'd just also like to briefly mention that there's a whole another part of Captura that's working on the R&D of the membranes for the electrolysis and then degassing the CO2. And I mentioned also really briefly earlier that those membranes will be 7 to 10 times more efficient than the commercially available ones, and are key to reaching our goal of $100 per ton, less than $100 per ton. Okay, so now you have an understanding of our process. Let's get into the real reason why I was invited to get this talk, which is about to talk about our MRV. So, Liliana mentioned and Nikhil put it in the chat, we recently published our MRV pathway, and it really serves 2 purposes. We describe our process there and our monitoring plans, and we really want to make sure that we're being safe and responsible, minimizing ecosystem impacts. And then the second purpose is to describe the MRV protocol for quantifying carbon removal from the ocean and the atmosphere. And this document holds some of our preliminary testing data from our first pilot, as well as laboratory experiments, and will continue to be updated with new data every 6 months or so. We're committed to being transparent in our process and welcome any feedback on the document. Okay, so there's essentially 2 primary outcomes of our technology that are pretty related. The CO2 that we directly remove from seawater and the CO2 that is absorbed from the atmosphere after our water is discharged back to the ocean. But before I go into more detail on that, I wanted to make a note that the most recent CDR pilot purchase price from DOE defines CDR as removal from the atmosphere or upper hydrosphere, which in that case, the quantity of CO2 that we remove from the upper hydrosphere, which is defined as the upper 200 meters, is accurately measured and has a negligible uncertainty. And most MCDR approaches have this large uncertainty in quantifying how much CO2 is absorbed by the atmosphere as a product of their process, and we're no different. So this is because the water in the ocean moves and mixes, and it's difficult to measure a small signal over a large background variability across time and space. So, our current available sensor technology is not capable of tracking the discharge plumes with direct observations. So, I know there's, ARPA-E recently had a CCO2 program where they're trying to galvanize some sensor development and model development, and I think that's great, and we really need that. So this is all to say, we need the models to estimate the atmospheric CO2 drawdown. We need a way to quantify additionality, so how much extra CO2 is absorbed from the atmosphere because of our process compared to what would happen naturally. And that can be done with high resolution regional models that are trained with our local monitoring data to help reduce the uncertainty in the quantity and provide high quality carbon credits. So we're collaborating with a number of groups who are working on developing these models that I've described. And one of those partnerships I'll describe a little bit more in a later slide. Okay, so some of the work that we're doing to address MRV in the pilot field trials is through a combination of lab experience, in situ observations, and modeling. One aspect of that is that we're doing these small scale tank tests to study how the effluent mixes with ambient seawater and how quickly the pH is diluted and how that concentration of PCO2 changes as it absorbs CO2 from the atmosphere. Using this tank, we can vary flow rates. We can look at different mixing ratios of effluent and seawater, and we can test different scenarios and optimize them for the pilot system. At Alta Sea, we have a suite of sensors and bottle sampling that we'll use to monitor several different physical, chemical, and biological parameters. And I have another slide that will describe that more in detail. And we'll continuously monitor specific variables to ensure that they stay within safe levels that are based on permitted processes that release water into the ocean already, such as desalination plants and wastewater plants. So for example, the pH of the water that we release will stay within the range of 8.5 to 9. That's within the limit of wastewater for California. We'll monitor dissolved oxygen to make sure that we keep levels around 5 milligrams per liter, which is high enough to not negatively affect marine organisms. And that's because when we remove the CO2, we also remove the dissolved oxygen. So we really just want to make sure we're not, creating any sort of dead zone around our operations. So additionally, we're partnering with a local aquaculture company at Alta Sea called Holdfast Aquaculture to study the biological impacts of our effluent. They will conduct experiments on local species of phytoplankton, mussels, oysters, sea urchins, and kelp, and basically look at different dilutions of our effluent to see what the effect is on their growth and their health. And then lastly, I'm going to show a little bit more about this later as well. We're working with the Southern California Coastal Water Research Project to do some modeling simulations of our process to estimate the CO2 drawdown. Okay, so the local monitoring is primarily to maintain ocean health and make sure we stay within the predetermined limits that I just described. This data will feed into the models that we'll use to estimate CO2 drawdown for MRV. And then I think I stole this from someone who presented about MRV. I think it was Simon Freeman, but he said it's like everything everywhere all at once. I don't know if anyone's watched that movie, but that's kind of how I think about MRV. We want to have everything everywhere all at once. And I mean, we don't have the capability to really do that yet, but we're throwing as much as we can at this pilot site. So we have this list of variables that I have on the right that we're measuring. And some of those are continuous parameters and some of those are discrete bottle samples. But we're doing sampling transects weekly in the channel. And basically that, that's all to serve to monitor the health of the channel. And then we'll also get an idea of which parameters are useful, which are not, so that we can take our lessons learned for future pilots and commercial sites. So this is the sneak peek that I was talking about for our, oh shoot. I converted this to a PDF. So now you can, this was a model, this was an animation, but now you can't see it anymore. Sorry about that. But anyways, it shows, let me back up as for a second. So this is our 3-month simulation from the Southern California Coastal Water Research Project, or SCORP. And they have a model that they validated in the Southern California Bight for, I think, the last 20 or 25 years. That has biogeochemistry. And so we are working with them, and they did a simulation for us that looks at 100 kiloton or 100,000 tons direct ocean capture system. And that would be located at this little blue dot right here. And we ran a pretty short simulation. It was only 3 months, but we were able to see a few really cool things. So first, we were able to see that there was a gradient induced of CO2 flux from the air into the ocean. And you would be able to see it a little bit better if I had shown the animation properly. But just trust me on this. And then, so we were also able to see during that time, it was 3 months, it was during the summer, so it's not surprising, but that discharge plume is able to stay in the surface mixed layer, which is what we want, because we want the discharge plume to stay in the surface, to be in contact with the atmosphere and draw down CO2 from the atmosphere. We saw that discharge plume, spread over time, and that specifically for at least pH, we saw that that pH of 8.5 to 9 that we release is a really localized increase in pH. So this contour around the location of the system is only 0.05 units, which is basically the observational limit of detection. And it's only covering a 3.5 kilometer squared area. So it's really not increasing the pH of a really large region. And then I want to focus on these two plots at the bottom here. This is the basically the additionality CO2 flux. So this is the difference between our, or a scenario where the direct ocean capture intervention was applied, subtracted by the baseline of what normally or naturally would happen. And so you can see it induced CO2 absorption from the atmosphere. And these are just different contours of, farther and farther away from that discharge point. And so the simulation was run in August, and then we looked at how much CO2 was absorbed in September and October. And even though 38 tons for September is not a lot compared to the 100 kiloton system, but we expect that there's going to be a kind of a exponential curve where it'll start to get more to a steady state eventually. But so that's kind of what we're looking at now with Corp, running a long-term simulation to see that how long that plateau takes. But we were really encouraged because in September it's only 38 tons per month, but then the next month is like 10 times as much, about 400 tons a month. So I think we're really encouraged by that, and looking forward to doing some more work with them. And I just wanted to finish by saying, our goal with our work at Alta Sea is to advance the readiness of Captura's direct ocean capture technology for deployment and commercialization. But our overall, long-term goal is to produce a scalable CDR method and remove gigatons of CO2 by leveraging the ocean's natural carbon cycle to mitigate climate change. And then, Liliana had asked, for some challenges that we may face, and so I just wanted to bring some up that maybe we can have for discussion. Is that there's no clear regulatory framework for CDR right now, or MCDR. And there's I think there's a need for the community to develop standards and guidelines for, both just these pilot deployments and eventually commercial deployments of CDR, and also MRV. Like those two things have to come hand in hand. So, thanks for listening, and I look forward to the discussion.
All right, Sophie, thank you for that. Yeah, I appreciate hearing about those regulatory challenges, and then also calling out the different roles for both monitoring and modeling, which we're hoping to explore in was probably our last session on MRV. So yeah, that was super insightful. Thank you. We have a bunch of questions in the chat, and I would like to turn it over now to Nikhil to get started with those questions. And so, yeah, Nikhil, go ahead.
Thanks, Liliana. Yes, there's a lot of audience questions, so let me get started straight away. First, maybe I'll ask a few specific questions to Erika and then to Sophie, and then go to the more general questions. So on the Equatic process, there were a number of questions. One was around the concern about chlorine generation with seawater electrolysis. Can you speak a little bit to that and how you address that?
Yes, I think that's a very good question. So chlorine generation we are addressing this by developing anodes that are oxygen evolution reduction select, so OER selective anodes. And this is a big part of our R&D efforts right now. So we do have a pathway to have oxygen evolution instead of chlorine generation.
Great. And there was a similar, concern or question about outgassing and how you can address that when there's going to be a differential in the PCO2 of the discharged water.
Mm-hmm. Yeah, the process is designed so that the PCO2 of our discharge is at atmospheric conditions. So it would have the same PCO2 as seawater. We could use atmosphere, so we can do the CO2 equilibration using air. So we'll have the same PCO2, or we could also use a higher concentration of CO2, but then only equilibrate that water until the PCO2 that is corresponding to atmospheric conditions. So, and I think to the point, yeah, the process is really designed so that we don't have any in-gassing or out-gassing happening outside of the plant.
Great, thanks. Yeah, that makes sense. And one last, let's just process-specific question. You have dissolved in organic carbon and some solid precipitation. Can you tell us, I guess, the ratio of CO2 that's drawn down in the solid versus the TIC?
Yeah, so most of the CO2 removed is in dissolved form. It's about 90% of CO2 removal is dissolved form, about 10% in a solid form.
Okay, all right, thanks. And Sophie, there were a few questions, and I know you touched on some of the modeling work, but the question around when the higher pH seawater that's returned to the ocean, you talk about having the capacity to remove the same amount of CO2 from the atmosphere. Can you elaborate a little bit on how that is confirmed?
Yeah, so basically, it depends on how to what extent that water is allowed to fully equilibrate with the atmosphere. So, if, like I was saying, we were trying to confirm that the discharge flume it stays at the surface, so it can maintain contact with the atmosphere. I didn't present about this, but there's a lot of factors that we're considering when we have our standalone system that can optimize the efficacy of the technology. So if we can deploy at places where the ocean circulation keeps the water at the surface, we can encourage that water to more fully equilibrate.
And then I don't know if this is a question that will require some forecasting, but can you talk a little bit about the difference between, and you mentioned that potentially direct ocean capture will get down to less than $100 a ton. Can you compare and contrast that with DAC, where the I guess, where direct ocean capture has some of the benefits versus the challenges of getting to cost and scale.
Yeah, I think I can try to answer this question, but I can also follow up with this if it's not satisfactory. But essentially, what I understand is that for direct air capture, you have to build all of these very large contactors to absorb the CO2 from the air. And for direct ocean capture, the ocean is the contactor. So that's where I think the advantage is for a direct ocean capture. And additionally, in the ocean, the CO2 is about 150 times more concentrated by volume.
Yeah, thanks. I think this question probably is to address to both of you and around the role that renewable power plays in penciling out and making sure the process is net negative. If it's critical, how do you ensure that your process is net negative? Do you need dedicated renewable energy, or what is your strategy there?
I'll start. So it is the renewable energy is one of the important inputs of our process, and for it to be carbon negative, we need renewable energy. So this is an important consideration for site selection. We look at the grid emissions factors for different localities, and this is one big consideration in addition to seawater, presence of rocks, as inputs to our process. It's important to note too, for Equatic, we also produce hydrogen. So hydrogen can be sold, or it could also be used as fuel to run the operations of the plant. So it could offset our electricity needs in that way as well.
Thanks.
Yeah, I'll just add that so cheap electricity is really good for our bottom line. And one of the unique aspects of our technology is that we can, the electrodialysis is the biggest electricity part of our process, and it can be built so that it's only run 6 hours out of the 24 hours. So we can use, whatever, if we're on the grid, we can use off-peak, pricing. And if we're, using renewables, we can use peak time of when the renewables are available.
Thanks. There were a number of questions around environmental risk, and I know both of you touched on that as being part of your MRV strategy. But there was one around how would you consider these risks as you start to scale? And will they be different and at different scales? And have you given thought to that?
Mm-hmm. So the environmental impact assessment that we're doing right now is for the next scale plant. It's for the 10 ton per day plant. So we are consistently thinking about the environmental impacts at a scale. Specifically, I'll just mention, so for Equatic, so we are concerned with total suspended solids specifically, because our process produces calcium carbonate. So this is one of the things that we've learned from our desktop assessment. So I think that is a good, so that desktop assessment is good in that way, that we could understand what the potential impacts are, right, before we do any discharge. We are also concerned about magnesium calcium concentrations if there's any perturbation, because we are precipitating calcium carbonate. We are replenishing divalent ions using rocks. So that's also one of the things we're thinking of. So yeah, but I think it's and to the point, it is important to think about this at scale. And I've always think about the next scale up.
I'll just add that we're trying to do as much as possible at this site so that we can see what the impacts are in as many ways as possible. And I didn't mention this, but we are part of Ocean Vision's Launchpad program. So, as part of that, we asked for advisors that can help us with the biological impacts side of things. And I think we've gotten some good feedback about that already. And, also with our partners at Scorp, we're, doing a lot of work with the biological impacts. And, the aquaculture testing that I mentioned, we'll be starting like really shortly. So we'll have some pretty cool results, hopefully, soon.
I think we have time for one, maybe two questions. Sophie, you touched on the permitting and regulations. So, and just tying that with MRV, what do you think are some questions or information needs that you need just from a regulatory standpoint? If you have those answers, and how are you getting those to help you get or speed up the permitting process? I mean, you can also, if you want to expand to broader challenges about MRV, feel free to expound on that as well.
Yeah, I think it's
not
just
MRV, permitting. Yeah,
I think it's just hard because CDR companies are trying to fit into existing permitting structures that are not built for CDR, where we are purposefully changing the chemistry of the water. And so I think if we want to streamline the process, and also sometimes permitting takes a really long time, right? And if we want to streamline the process, and these CDR companies were trying to move fast, so I think streamlining the process, having the community come up with standards will be really important, and then having the permitting authorities kind of involved in that discussion will help us kind of move quickly and responsibly.
Yes, Equatic right now our operation is so we operate under existing discharge rules, because our water is so. And I'm actually looking at the legal framework. There's a difference between like a marine engineering, where we change the ocean chemistry, versus dumping something or discharging something in the ocean that it can be considered as inert, can be considered as it's not really changing. There isn't any change that's going to happen to this plume of water once it's already in the ocean. So I think we fall into that second category. All of the CO2 equilibration would happen within the plant. So we discharge this body of water. In that sense, we could operate within the current framework. I think for we still are doing modeling. We're still doing this environmental impact assessment, because we are interested in the environmental impact of this plume, especially at scale, and also looking at the permanence. So looking at the CO2, so these commonly accepted, it's stable for 10,000 years if the residence time was just bicarbonate carbonate ions in the water. But we're looking at more on that, if there is any risk for re-release of that CO2 once it's been in the ocean.
Thanks.
I just want to clarify one thing. We are also, we also currently operate under the existing permitting, because we don't fall into any of the ocean dumping regulations either, because we're not adding anything to the water. I just want to clarify that.
Thanks. So I think that's about time we have. There were lots more questions that I'm sorry I couldn't get to, but thank you, Erika and Sophie, for answering those questions. And thank you to the audience for all those amazing questions. Liliana, over to you.
Great. Thank you so much, Nikhil and Sophie and Erika. That was really insightful and great to hear more about ocean chemistry. I learned a lot about ocean chemistry on this webinar. I would invite Sophie and Erika, if you are comfortable, to put your email in the chat so that those who have outstanding questions would be able to contact you and potentially get those answered offline. And it's just great to hear from two people who are innovators tackling these really, really complex solutions, and hear about the work that you're doing and even the challenges that you're facing, which hopefully we can solve in the next couple of years or so. All right, so thanks everyone for joining us. I know it's the beginning of COP this week, so I appreciate you taking the time out of your day. What's probably a really busy time of year to hear from these speakers and join our innovation exchange. We are planning, I think, what would be our final webinar on MRV to focus on the modeling component for sometime during January, probably late January. So please stay tuned for more details on that if you're interested in joining us again. Thanks again to our awesome speakers. And meanwhile, just want to wish everyone a great end of the year and hope to see you next time. Thanks, everyone.
Thank you so much. Thank you.
Thank you.
Bye.
Bye.